He coined the word synergy that we hear a lot. He invented geodesic domes. If you've ever seen a house built where the outside are all triangles, that's a geodesic dome. And when I was 12, I and two other kids spent 3 days interviewing him, asking him, or him asking us about how we saw the universe, and teaching us that the Euclidean geometry we're taught in school really distorts the way we see reality. So I see Mr. Andrews as being very brave as allowing me into your classroom to talk about how absurd the math he's required to teach you is. But we'll begin this off by, who knows what structure this is? Anybody recognize it? It's a cube. Right?
Yeah.
So it's a cube. But what do you notice about a cube made out of straws and strings? It is flimsy, right? Yeah. You see, the cube is built out of squares. And in many ways, our geometry that we get taught is made out of squares. And if you look at our real estate, they're generally made out of squares or rectangles or something with right angles. And Buckminster Fuller asserted that the universe comprises herself out of triangles. And by being taught the language of squares, actually gets humans to square off with one another. And his notion was that if we want to triangulate for sustainability, that we need to adjust the way that we are taught reality through geometry. If you notice that a triangle holds its own shape, and the square, or rectangle, doesn't. We're going to dive into some fancy words. In topology, they call a structure that holds its own shape statically indeterminate. You can see how the cube folds up on itself, but the octahedron, made out of all triangles, holds its own shape. And that's called statically indeterminate. Got a tetrahedron around here somewhere. Maybe our tetrahedron wandered off. We had a tetrahedron. Do you see a small little... Oh, well, I think our tetrahedron might have wandered off. Somebody might have wanted... Which is, it's awesome that somebody wanted... Oh, here it is. For a little while, I thought somebody had to have a little tetrahedron, which would have been adorable.
Had to have it.
This is the smallest building unit in nature, in the universe, the tetrahedron. The tetrahedron happens to be of equilateral sides. You can see something like a tetrahedron that isn't necessarily equilateral, because what we call regular in geometry is equilateral, but in the universe there's nothing exactly the same size. Like nothing exactly the same size. So what we call regular is a myth. In fact, from the beginning of geometry, what you are taught is real is a myth. You're taught about this idea of like a two-dimensional plane, right? And so if the chalkboard is, or the dry erase board is a two-dimensional plane, and I've drawn a circle on this two-dimensional plane, how many circles do we have? All right. Now, as opposed to using Euclidean geometry and insisting that this be a two-dimensional plane, I want to bring us into topology and to have us thinking four-dimensionally for the next half hour. I'm using this as a preparation for a presentation I'm giving in April at the Empower Autism, Autism in the Pursuit of Happiness, and Four-Dimensional Thinking, where I'm going to be talking about how Buckminster Fuller taught me four-dimensional thinking. And when I was 12 and I was with the two other kids, one of the first things that he asked us to do was he took a piece of paper and he asked us how many circles were on the piece of paper. And I think we all agreed that there's one circle. But the idea that this is a plane is a misnomer, because this piece of paper has length, width, and height, albeit small. And it exists in time, so that's four-dimensional, right? I mean, even the ink saturating into the pores of the paper has dimension. topology is geometry in 4 dimensions. And in topology, the basic distinction that we start with is a solid versus a torus. This is actually a torus because it's got the holes in it. But like a donut or a bagel is a torus, where the tennis ball is a solid. So, forgetting that this is 3-hole punched, if this is just a piece of paper, can you imagine that this as a solid is kind of similar to the tennis ball as a solid? They've got length, width, and height. They exist in time. So I want somebody to help me out for a second. Volunteer. Fantastic. Take the tennis ball, and I'm going to ask you to draw a circle on the tennis ball.
Okay.
So, anybody disagree she's drawn one circle? All right. Would you fill in the circle? So she's filled in the one circle we have. Yes, your name is?
Christina.
Christina. So Christina, if you make the circle a little bit larger, if you'd enlarge that circle, if she were to keep enlarging the circle that she has there, at a certain point, that circle would become so large that it would be the equator, that it would cover half the ball, right? So if she kept making the circle even larger, it would continue to consume the ball, right? And we would wind up with, that's large enough, thank you, Christina. We'd wind up with something that looks like this, right? So this begs the question, when you look at billiard balls, when you look at the balls on a pool table, is an 8-ball a black ball with a small white circle on it, or is it a white ball with a black circle that is so large it almost encompasses the entire ball? Buckminster Fuller's point was that you can't draw one circle. It's impossible. Euclidean geometry trains us to look at the microcosm of the circle, the inside of the circle. But the function of the circle is the division between the microcosm and the macrocosm. And so, at minimum, any circle is at least 2. This changes the way one will see the world, because you can no longer have the traditional construction of 1. Any distinction of 1 is actually a separation and truly means 2. The opening poem of the Dao De Jin, a collection of 81 poems, the second most published book in the world next to the Bible, talks about the 10,000 names and talks about the illusion within a single name, and ends with the stanza that those that are bound by desire will only see the outward container. And what Buckminster Fuller was talking about was that the way we are taught geometry teaches us to think small, to see the microcosm. And his goal was to help me and help others break through that small thinking and to start with universe and work in. Now, much of the language that we're taught from an early age is disorienting. For instance, how many of you saw the sunrise this morning? A few people? How many of you saw the sunset last night? How many of you have ever seen the sunrise? Okay. How many people have a dog or have ever seen one? That notion of seeing the sunrise, how disorienting is that? The earth is spinning. The metaphor of the sun rising suggests that the earth is still and the sun is going around us. When in reality, the earth is spinning And when we begin to see the sun, we call it a sunrise. Because when we had a flat earth mentality, that was the language that was appropriate for what we imagined the phenomenon to be. But we use these outmoded vocabulary words to introduce young minds to the way the universe works. We tell them, oh look, the sun is rising. Where he suggests if we use the word sunset for sunrise, or sunclipse for sunset, that it would better orient the young minds as we introduce them to this thing that we call Earth. Bringing it around to the geometry, Bucky is known for geodesics, which largely takes the icosahedron and then breaks each of these triangles into smaller triangles, and that way you can get a sphere. Epcot Center, you guys have seen pictures of Epcot Center? That's a geodesic dome. The most fascinating thing to me about an icosahedron or other geodesic structures is that there's more energy pushing out than gravity pulling down. So that a 70-year-old geodesic house is more likely to have a strut pop up than a roof fall in from gravity. That's a different way of seeing energy in the universe. What Buckminster Fuller did while he was at Black Mountain College was invent the geodesic dome. And he was invited to Black Mountain College right after he came up with a new style of map called the Dymaxion Projection that's based on the icosahedron. And Mr. Andrews, if you would turn on the overhead, the kinds of maps that we see of the world, like if we look at the one in the back, that's not a Mercator projection. I forget the name of that specific projection. But whether it be a Mercator, which is more square, or that one, which is kind of rounded on the side, we're taught largely without a globe that that's what those continents look like, right? We don't really think about how much distortion might be there. Downstairs in our school, there's a Mercator, which is a rectangular map, and it says the world at night. And it's kind of fascinating to me because it's all of the lights and the darkness around Earth. And yet, when is Earth always dark all around it? Never. So, when you take a Mercator map, what's a circle in the center winds up being this type of shape at the bottom. So that Antarctica or the countries where we're at closer to the top or the bottom are going to appear far wider than they would be the continents and countries that are around closer to the equator. Could we go to the one where it has the... Here's what it would look like if we took the human face. Look at this kind of distortion. And then let's look at the one on the far right, which is how the Dymaxion projection goes. So this is an icosahedron. This is a globe, which is a sphere. And it's a matter of taking the sphere, putting it on, projecting it on the icosahedron, and then you can lay it flat. And that is way more accurate than that distorted face that we show. And that kind of respect for accuracy and a better reflection is part of what Buckminster Fuller was talking about in terms of how much we are blinded by the words that we're taught to use as we learn Euclidean geometry. Because we're taught to see squares and right angles. And in nature, there are very few naturally occurring squares and right angles. Now, many times things like the icosahedron, the octahedron, the tetrahedron, people here have heard of these referred to as sacred geometry. Sometimes people talk about these as sacred geometry, sometimes they're referred to as Platonic solids. But until the 20th century, people would say that all of universe had to be created as it is perfectly now because it's impossible for the Platonic solids to unfold from one to another. And while I don't want to enter into a debate of creation versus evolution and those elements, many that hold towards creation believe that there is evolution that can happen within that scenario as well. But the notion that the Platonic solids can't unfold through one another, Buckminster Fuller said they absolutely can, and they do. And as we develop more powerful microscopes, we see that they do. But what Bucky took is what's called a vector equilibrium. And this shape allows us to see how something that would be the shape of an icosahedron, if we were to fill in some of the struts right around here, can collapse into an octahedron, which can collapse into a tetrahedron. And so the tetrahedron, the smallest building unit in the universe, can unfold up through the Platonic solids. And he came up with this from looking at some of the old technologies around stacking cannonballs. And Mr. Andrews went out of his way to ask a friend for tennis balls. But if you were to want to surround a tennis ball, I'm going to ask you to play if you don't mind. Your name is? Henry. How many tennis balls will it take to surround one tennis ball with other tennis balls? I don't know, 9. 9? All right. Other guesses? 5, I hear. 6, 7? It sounds like we're about to get an announcement.
Nah, just okay. Lunch change.
But let me ask you another question. How many of you think that it will be an exact number of tennis balls, or how many of you imagine we might need to cut one up? All right. The way that it actually works is if you take one and let's surround it by tennis balls. Six tennis balls perfectly surround one tennis ball. Now, if we want to cover this, and this was one pattern that they used to use for stacking cannonballs, we could put 3 on top. You see what I'm saying? And it holds its shape. So we've got 1 surrounded by 6 and 3 on top. Now let's imagine for a moment that we could pull out that 1 in the center, and we just have the 6 and the 3. And we go back to the vector equilibrium, and notice that there are 3 points on the triangle that's on the top, and 6 points around this, and another 3 on the bottom if we were to put 3 more underneath. If they were glued together, it would hold that shape. But through the way that solid circle spheres can stack, creates this pattern of the vector equilibrium, which demonstrates how nature can fold and unfold through the Platonic solids. I can't tell if this is exciting or boring to you guys. For me, it's a little mind-blowing at times and fun to see some of the patterns of how a universe works that we're not necessarily taught in traditional Euclidean geometry. Is this good for you guys?
Yeah.
All right.
How does it fold? Like, how does the universe fold?
Well, I am no microbiologist or physicist for that matter, and yet there are times that proteins will fold and unfold, and that microbes will create these kinds of structures. In terms of the how, I really don't know. What I do know is that when Buckminster Fuller was in his 70s, he predicted that when microscopes became strong enough, that we would find 60-sided molecules. And molecular biologists were like, oh, Bucky, that's so cute. You know, you're an architect and you write that poetry, and but you really don't know anything about microbiology and that kind of microphysics. And Bucky held his own, and he was like, as above, so below. We've got 60-sided structures that are geodesic. If we imagine that going smaller in the microcosm is going to reflect the larger in the macrocosm, when our microscopes are strong enough or conditions are right, we're going to see a 60-sided structure in microbiology. And within 15 years after his death, they identified the C60. Sometimes I just cry out of the blue. It is whatever it is. But Bucky was vindicated. The 60-sided carbon molecular molecule, they often call the buckyball or the fullerene. And it's a 60-sided molecular item. He was right. Every once in a while, tears just come through me. And they pass quickly, and I'm grateful that it's no big deal to you guys. I'm autistic. I know when I say that many times, people's first reaction is to say, you don't look autistic, which is absurd to me, because I am autistic, and I look how I look. So it's impossible for me to not look autistic, since I am. In a class earlier this morning, I said I'm autistic, and a kid said, you don't look autistic. And I perhaps squared off with him a little bit, and I said, and you don't look ignorant, and yet here we are. It discomfited him a little bit. He needed to talk over me a little bit for a little while. But they refer to autism as an invisible disease, which I find offensive because I don't think of autism as a disease. It's just a different operating system. Part of what makes my operating system different is perhaps natural by birth. Some of it might be environmental. And other parts are that I can have focus and have a certain savviness with mind that I can't teach others. But I can notice patterns and teach you guys how to do some stuff in your head that might appear magical or like a savant. When I was 16, I used to do a mind readings and powers of the mind routine where I would present myself kind of as if I'm a mathematical savant. And while I'm not a mathematical savant, I used to work in quantitative research, and I can do things in math that even amongst those that are really, really good at math, some said, you're the fastest I've ever seen at that. So thank you for intuiting my wanting to get that. There is a fun magic thing called a magic square that I'm going to show you in a moment that isn't it's more easily taught and less usable than a shortcut I'm going to teach you guys right now. If I were to ask, what's your name?
Daisy.
Daisy, do you feel comfortable doing a multiplication thing on the board?
Yeah.
Awesome. I want somebody to, I'm going to ask you to square the number. So when somebody's going to name a two-digit number in a moment, and you're going to do it on the board, and I'm going to do it in my head. So who wants to pick a two-digit number? All right. And give us the two-digit number. 37. 37 squared, 37 times, yeah. 37 squared is 1,329. Would you double check? Right, and so times 37.
There's one that works a better.
What did you say that was?
That's. I think I messed up. I think I
could have messed up.
I believe yours is correct. I think I recollected myself saying 49 and not 69. Pardon me, 1,369. But let me show you guys how I got there that quickly, even though I messed up. So now I'm going to show you an easier way, if you will. Still use the pen. And I want you to multiply. I want you to multiply 33 times 40, but put 33 on top and 40 on the bottom. Who could do 33 times 40 in their head? Great. But go ahead. Oh, I'm sorry. It was, fuck. It's supposed to be 34. And I dropped an F-bomb.
Jeff told me it's the one thing I'm not supposed to do.
All right, I give you one warning.
All right.
Maybe two.
I can tell you guys are all traumatized. You've never heard that word before. You've never used it. Cool. And how much did we go up from 37 to get 40?
30.
All right. What's 3 squared?
9.
Add 9 to this. Doing math with zeros is easier, right? So let's say that you want to square 25 squared. And you go up to 30 and down to 20. 20 times 30 is 600, plus 5 squared is 625. Remember FOIL, first outer, inner last? This is simply using an application of FOIL that allows us to do multiplication with zeros because zeros are easier to do than using the full-on numbers. Cool. Let's give her a round of applause for that. And now I'm going to show you a demonstration based on, it's called a magic square, but I'm going to use some help of some external music. And
One that works. I'm going to get rid of the other.
okay, this is a different color, but we'll use this one. You've probably heard about the left and the right side. You got a question?
How old were you when you figured out that multiplication?
I was, I believe, 13 years old when I met Arthur Benjamin, who at Abbott's in Colon, Michigan. There's an annual magic conference, Colon's Magic Gathering, and Arthur Benjamin did what he called Mathemagic, and you can look for him on YouTube, and he can now square 8-digit numbers in his head. But as a 13-year-old, he taught me how to square numbers in my head. With some practice, by the age of 15, I could square a 4-digit number in my head. It takes practice. When I was in my peak in terms of math in a younger mind, because your minds will change as you grow. My mind was probably its savviest with math when I was about 15, 16. And you could give me a 3-digit number, and I could follow that process and square it in under 3 seconds. Arthur Benjamin could do a 4-digit number that quickly. He had to create a new form of mnemonics in order to remember the numbers for doing an 8-digit number. And he's in the Guinness Book of World Record for having squared the largest number in his head. So I was 13 when I first learned how. When I was 16, I needed to recreate myself as a magician. When I was 14, I was performing at the Magic Castle. I was the youngest performer there to have an act that was a talk act. There was a guy named Danny Scott who was a genius 13-year-old magician who was the youngest to perform there with a silent act with doves. And so the big challenge for a nightclub to have a 14-year-old on stage who's talking is that I might drop F-bombs, which would be seen as the corruption of a teenager, which would jeopardize their liquor license. So there I really had to promise to not drop F-bombs on stage, even though off stage I sometimes did. I'm sure that nobody in this room has ever used the F word. I'm sure that that would be a sign of corruption, but they get stringent when liquor licenses are involved. So I did this routine of like a bumbling magician, and I would do these tricks that kept failing, and it was really cute when I was 14. And it was cute through most of the time that I was 15, and then it was weird. Within like 3 weeks, I lost that cuteness, and suddenly what had been getting standing ovations, because at the end of the routine, everything winds up coming and working together, and I produce a chicken. And I was getting standing ovations, and I found I really loved getting standing ovations when I was 15. And then suddenly my act was dying. It was like I'm on stage, it's the same act, it's 3 weeks later, and audiences are talking. And there was just something in me that changed. I don't know if it was my voice or whatever, but it felt like it was overnight. It was in less than a month. And I had to recreate myself. And so the way that I recreated myself was in doing magic that looks like mind reading, sometimes it's cold reading, and doing that math that I'd learned to do in my head and showing it as powers of the mind. And the way that I would close my act was with a magic square. And I would explain to the audience about how you're familiar with the left and the right side of the brain working together. And if the right side, the creative side, is entertained, it somehow allows the left side, the analytic side, to work more efficiently. And so in a moment, would you mind choosing a number in a moment? In a moment, I'm going to ask you to choose a number between 20 and 100. And you can choose any number you want in there, but realize if you choose a number like 98, it's going to be a lot tougher for the other people in the room to follow along. And when I say that, sometimes then somebody goes, well then 21. And 21 is also a little silly, not silly, but I'll wind up repeating numbers. So if you chose a number between like 30 and 60, it makes it easiest for most people to follow along. But trust me, if you chose 4,285, I could make this work. So in a moment, Mr. Andrews is going to play some background music that's going to stimulate the right side of my brain, and I'll see if I can't make this magic square, make all of the numbers interconnect with each other. In a loud, clear voice, what number would you like me to use? 43. Mr. Andrews, maestro of music, please. If you have a calculator and you want to add along with me, you're welcome to do so. Across the top row, 23 and 1 is 24, plus 12 is 36, 7 is 43. You chose 43. 11 and 8 is 19, plus 22 is 41, and 2 is 43. 5 and 10 is 15, 3 is 18, 25 is 43. 4 and 24 is 28, 6 is 34, 9 is 43. Try up and down. 7 and 2 is 9, 25 is 34, 4 is 43. 12 and 22 is 34, 3 is 37, 6 is 43. 1 and 8 is 9, 10 is 19, 24 is 43. 23 and 11 is 34, plus 5 is 39, and 4 is 43. Try the diagonals. 9 and 3 is 12, 8 is 20, 23 is 43. 4 and 10 is 14, 22 is 36, 7 is 43. Try the center set of 4. 8 and 10 is 18, plus 3 is 21, 22 is 43. Try the corner blocks. 3 and 6 is 9, 9 is 18, 25 is 43. 23 and 1 is 24, 11 is 35, 8 is 43. 5 and 4 is 9, 24 is 33, 10 is 43. 7 and 12 is 19, plus 2 is 21, 22 is 43. Try the top 2 and the bottom 2. 6 and 24 is 31 is 31, 12 is 43. Try these 2 and these 2. 2 and 25 is 27. 5 is 32, 11 is 43. Try the top set of 4. 1 and 12 is 13, 8 is 21, 22 is 43. The bottom set, 10 and 3 is 13, 6 is 19, 24 is 43. These 2 and these 2, 25 and 9 is 34, 4 is 38, 5 is 43. These 2 and these 2, 7 and 2 is 9, 11 is 20, 23 is 43. My favorite are the cross diagonals. 6 and 25 is 31, 1 is 32, 12 is 43. 5 and 24 is 29, 2 is 31, 12 is 43. Evenly out of 4 corners, 7 and 23 is 34 is 34, and 9 is 43.
How does the music end? How'd you do that?
Timing. I was a geek in high school and did it hundreds of times. So, that's fun. And it's more impressive than that squaring the 2-digit number in the head. But this is actually easier to teach and learn. You guys want to learn this?
Yeah.
So, it's based on 34. Because if you use the numbers 1 through 16, this works out that many ways. Now, this was again something that Arthur Benjamin introduced me to, a variation of this, but he made me work for it. He showed me a variation of this, and he wanted me to see the underlying patterns. He wanted me to take away the numbers that were the distraction to see the pattern. And so, I'd love a volunteer to replace these numbers, or to put in each one of these squares the corresponding grid. Anybody willing to do it? I can explain more. Great. So that, for instance, 16 would be D4. So where you see 16, yep, you'll put D4.
Oh, so corresponding to, okay, that makes more sense.
Great. While he's working that out, I want to get back to what Buckminster Fuller was saying about language. Buckminster Fuller was talking about the disorientation that happens when we're taught to see the sun rise. Because when you're told the sun is rising, it gives you the sense that you're being stationary, but the sun is moving around you, right? And when we're taught that there's one circle, and so we all agree we only see one circle, it teaches us to see the microcosm and not the macrocosm, not the division between two, not that the label is actually a distinction of two things. We treat the label as if the label were real. And yet it's just a label. And in Eastern philosophies, they have an interest in loosening the brain from such a strong connection to specific labels. Thank you. Buckminster Fuller said that his word synergy was what he imagined to be his greatest gift to humanity. And the reason why he thought synergy was his greatest gift to humanity wasn't the natural philosophy proof that he published in the name of synergetics, but for the psychological benefit of the word synergy. Now, we're familiar with synergy from bullshit bingo and the idea that it's used in corporate meetings of we want more, we want more. It's almost, synergy's become a synonym for greed. That synergy is we need to be more profitable, or synergy is we need better results, or synergy is whatever and whatnot.
Better test scores.
Better test scores. What synergy is a restructuring. What synergy is, when you add graphite, like from a pencil to steel, and you get graphite steel, and suddenly steel is super steel and able to build skyscrapers, what's happened to the steel is that the molecules of the steel have restructured. When water turns to ice, the molecules have restructured, which is great if you want coldness, and sucky if you want the water to flow through your pipes. So synergy isn't necessarily the greater outcome, as is often described, and Bucky talks about restructuring humans, where if you take 20 individual shoemakers, and it takes them 2 days to make a pair of shoes from scratch, but you reorganize those 20 shoemakers and you create specialists, those 20 shoemakers can wind up, if one person is just focusing on making heels and another person is just focusing on different parts of it, those 20 shoemakers can suddenly create 80 handcrafted shoes in a day through restructuring the way that they're working together. Which is great if your sole goal is to get more shoes, but perhaps not so great if you're gaming for quality of life. And so a word like synergy isn't always positive. It's simply a restructuring. And a lot of the definitiveness that we get taught in math is more arbitrary and heuristic. Now the patterns here, we've replaced, based on 34, and these numbers, and thank you for the help in doing this. I want you to notice, let's imagine for a moment that A, B, C, and D were numbers. In any given direction, you're either going to have an A, B, C, D and a 1, 2, 3, 4. Or for some of the other combinations, you can have A, A, D, D. Because an A, A, D, D would average out to a 1, 2, 3, 4. So can you see how by using these numbers, you can see a 1, 2, 3, 4 and an A, B, C, D in any of the different patterns that I had presented before? Question?
Synergy is like give and take, kind of?
Synergy is the word for the restructuring. There are times that things restructure. In the process of that restructuring, there's the word perturbation. Culturally, virtually everyone agrees that right now we're going through a global cultural perturbation. We are unsustainable with 6 billion, 8 billion, billions of people on this planet. And with the amount that we're destroying and using energy-wise, we can't have this quantity structured as we are for the next 100 years. It just won't work. There will be some sort of restructuring of humanity. Going through that restructuring, should we survive, that restructuring will be called perturbation. In chemicals, when you add the graphite to the steel and you blend it together, that steel bonding with the graphite is a form of perturbation. Back to showing off with math. This pattern, you can see the interconnectedness of these elements. Now, to make it so that it's easy for you to memorize and do in your head, we're going to use this pattern, but we're going to eliminate some of the numbers with an algebraic equation.